together while I was there as a postdoc. And we asked this question about how we could think about how machine learning should be used in social science research. And we had all been doing this a bit in our own research. And we came together to think a little about like, what are the principles that bring together the way machine learning people talk about doing analysis with the ways that social scientists talk about doing analysis. And so this paper is now available. It's in Social Science Research in this special issue that Weiwa edited. And so you can go, we'll send the slides around later. There are links at the bottom of this slide to our paper. You could also just Google it and get there. And there's also a link to the SOS archive version, which you can access if you don't have like a library subscription to social science research. So mostly today, I'll just be giving like a high level overview of our thinking, and then I'll leave it open for questions at the end. And there's a lot more information in the paper if you want to read more afterward. So there's a few things we'll talk about today. So one is that the whole idea of doing statistical analysis has to begin with a task or a goal that we want to accomplish. So I'm going to start out by talking a little bit about how we can have clarity about that goal. Then I'll talk about some statistical ideas like the bias variance trade-off, some machine learning ideas like how we can automate the selection of an estimator, then how machine learning and statistics both can lead toward interpretable estimates. And I'll return at the end to come back to this question of task clarity for where we think about doing new kinds of prediction tasks in new populations. And I should really give credit to Nanam for making these slides for a previous workshop. So the reason they're so beautiful and nicely structured is because Nanam made the slides. So let's start out by talking a little bit about task clarity. In both statistics and machine learning, there is a shared task. That task, to take a simple example, could be drawing inference about a target population from a sample. So in statistics, we think we have a sample of data and we want to learn about some population parameter. And in machine learning, we might have a training sample and we want to use that training sample to learn an algorithm that then will then apply in a test sample or in future population cases. So the two ways that people think about this can have different words, but they're actually often accomplishing the same goal. So in the statistics perspective, we often talk about estimation of unknown population parameters. In the machine learning perspective, we often talk about prediction of out-of-sample cases. So I'm going to walk through a particular case here, and we're going to think about how a social scientist or a statistician might frame that task in terms of estimation, and how a machine learning person might frame it in terms of prediction, and how you can really see those two as accomplishing the same goal. The running example will be looking at the academic performance of students nested within classrooms. So for those who like to speak in math, I'm going to say this in math, and for those who don't like to speak it in math, I'll also say it in English, so you can follow along in the math or in the English or in both. So our research goal here is to estimate some unknown quantities. So for each student indexed by I, there's a test score, Y sub I. That student is also nested in a classroom. So we're going to use capital J sub I to indicate the classroom in which student I is a student. And our goal is to estimate the mean outcome. We're going to call that theta sub little j, which is the expected value of test scores over all students I, such that the classroom of student I is the value little j. So this is just the average test score in classroom little j. I'm now going to show you that goal framed more like a machine learning person might put it. So at the top part here, we have what we might call a training sample. So we have a set of students drawn at random from some population. So you see that we have students 1 and 2 who were sampled for the training sample, and they're in classroom 1. Students 3 and 4 are in classroom 2, and 5 and 6 are in classroom 3. For these students in our training sample, we get to observe their test score outcome. And because of that, we can now accomplish a learning task. So we can take some algorithm, so this could be like a statistical estimator or a machine learning algorithm, to learn a mapping between that predictor and the outcome. So when I see that a student is in classroom 1, here the 2 students in classroom 1 have test scores 84 and 89. So I might predict like 86.5 when I see a new student who comes from classroom 1. Now, a machine learning person would look at this and say, we should think about our task as prediction. So there's a whole next set of students who are also in these classrooms who were not sampled for our training sample. So when we were learning the prediction function, we didn't get to see the outcomes of students 7 or 8. Those are like question marks on the right. And so a machine learning person will say that what we're trying to do is learn a prediction algorithm in the top and then make predictions for the other cases who appear in the bottom part of the figure. The reason this is the same as statistics is because the best prediction function is going to be the mean in those classrooms. So if we really knew the average test score in classroom 1, then that's what we should predict down at the bottom, at least if our error metric is mean squared error. And I'll come back to that one in a minute, but mean squared error is a common error metric in machine learning that's also very similar to many statistical estimators like ordinary least squares. Okay, so I just said if you knew the mean score in each classroom, then the best estimator would be to predict that mean score for every classroom. But in fact, we don't know the mean test score in every classroom. We only sampled like 2 students per classroom. And so we're pretty uncertain about the true mean test score in each classroom. The bias variance trade-off helps us navigate this uncertainty. So the bias variance trade-off says that the expected squared error of an estimator. So think here of theta as like the expected as the test score on average in classroom 1. Theta hat is our estimate of that average test score in classroom 1. So if we sampled students 1 and 2, then students 1 and 2 help us estimate theta hat, but maybe really students 1 through 10 are all part of classroom 1. So we have a squared difference between our estimate and its true value. And we want to say something about the expected value of that squared difference across hypothetical repeated samples where we would re-estimate the mean score in that classroom. So it turns out that that squared difference can be decomposed into 2 components. So the first component here is squared bias. So this is the difference between the expected value of our estimator across repeated samples. So on average, if I repeatedly sampled 2 students from classroom 1, what would my estimate be on average for the mean score in that classroom? Minus the true value for the mean score in all the students in that classroom. So that's our bias term that could then be squared to make it positive. Then on the right, we have this variance term. So this variance term says, if I do a bunch of repeated samples from classroom 1, how much do my estimates in those repeated samples vary? Like how much do they have a spread around their expected value, like the mean that I would estimate across repeated samples for that classroom? So these 2 properties are nice to think about because bias is like how wrong I am on average, and variance is like how spread out my estimates are across repeated samples. I think often social scientists sort of cringe at the word bias. I think statisticians do also. We would think, oh, we don't want to have a biased estimator. But in fact, sometimes the estimator with the best expected squared error is going to be a biased estimator. So to take a running example here that we're working with, one estimator you might consider is the simple mean estimator. So this says I'm going to look at all the students I sampled in a particular set of cases, like those in classroom 1, and I'm going to just take their mean score and report the average. Another estimator that would be familiar to statisticians is a hierarchical linear model. So this looks like really complicated math, but it's actually not terribly complicated in terms of intuition. So the hierarchical linear model estimate says at the left, I'm going to start with that simple mean score. So for all students in classroom little j, this could be like classroom 1, just take the average score of the ones I sampled. Then this term on the right is known as a shrinkage term. So you see at the far right here that this has the deviation between my estimated mean in classroom j and y bar, which is the grand mean over all the cases I sampled. And so you might want this shrinkage term if you think that all the classrooms have like something in common, so that when you see one that's very far away from all the others, you might worry that it's far away by random chance, and it would be better to pull it in toward the central tendency of the whole data set. The degree you might want to pull it in is this fraction here, which looks like the most complicated part of what's going on. So that's proportional to the amount of variance within classroom J divided by the sum of the variance within classroom J plus the variance between the classrooms. So basically, when there is a lot of variance within classroom J, so this term at the left is really big, and there's very little variance between classrooms, this term is really small, then we should shrink classroom J like really far toward the grand mean y bar. And when there is very little variance within classroom J, we have a really accurate estimate of the score in classroom J to begin with. And so then we would want to have very little shrinkage. Okay, so why did I walk through all that jargon? I walked through this all because it's helpful to see where there's a parallel between the way statisticians think about the bias variance trade-off and the way machine learning researchers think about the bias variance trade-off. So here at the top, I have the expected squared error of our estimator across repeated samples. So this tells me, on average, what's the squared difference between my estimate of the class-specific means and the true class-specific means. And we see at the far left of the plot that when we have no shrinkage, when we just estimate the mean of the cases we sampled in each classroom, then we have relatively high expected squared error. And that occurs because we have low bias, but high variance. Like if we didn't sample very many kids in each classroom, we might have really uncertain estimates for each classroom. Then at the far right, we have the other extreme, where we pull everyone in toward the overall mean very far. When we do that, we also have very high expected squared error because we have extremely high bias, even though our variance goes down to 0. And so in between these extremes is the shrinkage chosen by a hierarchical linear model. This says we're going to take each classroom and estimate them to have different means to the extent that the data support it, but we're also going to pool some information in a principled way across those classrooms. So we'll regularize or shrink them all toward the grand mean. And I think this is a nice example because machine learning researchers are always trying to minimize a loss function. This is some measure of how poorly your estimator is performing. And one common loss function is expected squared error. So machine learning researchers have whole techniques to try to empirically estimate their expected squared error and try to find the bottom of this curve. And this particular example is one where the theoretical result that statisticians might know about this partial pooling hierarchical linear model, it actually corresponds to the correct answer to the machine learner's way of thinking about the problem. So the takeaways here are that there are these parallels. If you're familiar with one of these ways of thinking, you can probably see how it would work in the other way. And the other takeaway is just that we sometimes want to have a biased estimator because it might actually be better than an unbiased estimator. The next thing I want to talk about is data-driven estimator selection. This is an idea that's really much more a machine learning idea than a statistics idea, though I think actually both sides have some similar ways of thinking about this problem as well. So the question here is, suppose you have many different possible models or machine learning algorithms that we could apply to a research question. Then how do you choose which one to apply? And this may seem like a really relevant question today because as statistics and machine learning really grows, the number of estimators available to you just gets bigger and bigger all the time. So we have so many things to choose from. How do we choose which one to use? So a machine learning answer is that to the degree that the data can inform the choice of estimator, machine learning approaches are great because they allow the data to speak. And the way they allow the data to speak is through a loss function. This will again look a bit mathy, but I'll also say it in words. So a loss function measures how poorly a particular estimator is performing, or you could think of, on the converse, how well it's performing. So here the loss function is this script L of a particular estimate, theta hat S, which has been estimated in a sample S. This is like the training set of cases we used for learning our algorithm in the beginning. And here I'm going to show you expected squared error. So this is the expected value, that's the mean, over all units I, such that I is not in S. So a key principle of machine learning is that when we learn a function on one sample, we should then evaluate its performance on another sample. And there are some good statistical reasons for doing this. It's especially helpful when you have an algorithm that really goes hard at trying to map the features in the data and learn the patterns in a complex way. In that case, it's really helpful to go evaluate your estimator on a new sample. So the loss function here would be, we might say, let's take our predicted value. So for unit I, we see its predictor vector, or sometimes they call it a feature vector X. So this is the things that the algorithm uses to make its prediction. And then we're going to make a prediction for unit I. So that's theta hat of X. Then we'll see how far is that predicted value away from the true outcome Y that was realized for unit I. Then because we're concerned if these two are far away, we want to square this term so that having a large value is bad. Then the loss function is the expected value of this squared error across hypothetical repeated samples and across units who are not part of those training samples. In practice, we often can't know the loss function perfectly. Here I'm talking about the expected value over a whole population of units, and we maybe didn't sample all those units. So instead, we often work with an estimated loss function. So I'll put a little hat on top of the L here to denote that this is now an estimated value for this loss function. This equation will look familiar to those who are familiar with machine learning. So this is just the average value in some S test. That's a set of units who are being considered a test sample. And they're a set of units who were not available to the algorithm for training. So it's the average over the test sample of the squared error from a model that was built using S training. So we built a model using S training, made predictions for everyone in a test set, S test. Then we squared those prediction errors and took the average over the test set. Now, this is a case where I think machine learning folks can learn some from the statistics folks. So I think a lot of people in machine learning do this just because they think it's what we do. We always take a test set and take the average squared error in that test set. And it's helpful, I think, to keep in mind that the reason we do that is because we care about this unknown loss function in the whole population where we might be trying to make our predictions. Okay, so what does this look like in practice? Here is one hypothetical simulated case. So we simulated this really wonky looking function that we just did for illustration purposes. So this is a curve that kind of bends up and then flattens out along 1. So whenever x is greater than 4, the mean value of the outcome is always 1. And then the data points are randomly drawn about that curve, so that in any particular sample, you might not be able to estimate this curve perfectly because it depends on which cases you happen to draw in your sample. So we then considered a series of estimators. So these range from, at the top left, ordinary least squares is a very simple classic statistics estimator, all the way down to a generalized additive model here, which is an estimator that's designed to estimate smooth curves by sharing information locally across points that are nearby to each other on X. Now, because this is a simulated case, you can look at this plot and immediately see that the GAM is the one that's doing the best at approximating that true gray curve. But in real data analysis, things are not simulated, and you wouldn't know where that true gray curve was. You could just estimate all these models and then have arguments all day long with your colleagues over which estimator is the better one. And everyone would have their own opinions. Some people would have favorite algorithms that they like all the time. It'd be hard to decide what was the best. So this idea of an estimated loss function in a test set becomes super helpful. So before having all your arguments, you could split your sample into 2 sets, a train set and a test set. Then you can learn the prediction function in the train set while keeping the outcomes of the test set hidden away. Then you make your new predictions in the test set. So everyone has to commit to their choice of algorithm before they open up that test set. They make their predictions and then take the expected squared error of those predictions. So we've done that exercise, and down at the bottom, I'm showing you along the x-axis, the mean squared error in the test set for the algorithms over here. And we can see that the lowest mean squared error is for this GAM, which visually we can see is very good at approximating that kind of wonky curve that we simulated. We can also see that some models, like the linear OLS model, have very high mean squared error. And looking at the curve, you can see why, because they're very far from that true curve. So the notion of using a train test split is an extremely powerful notion because it helps us resolve among the many candidate estimators we might use. I think it also makes it easy to pivot from classical statistical estimators and toward machine learning estimators, because when you have a given predictor set and a given outcome, it's not really clear why you would prefer one algorithm over the other. And this is a way to actually just try them and empirically see what's doing the best. So if you find that a machine learning approach can predict better than your classical statistical approach, then you'd have to come up with some other reason if you were going to continue working with a statistical method. So I am in the camp that generally thinks in that case, it's often worth pivoting toward machine learning methods that do better at approximating unknown functions and can predict better for the kinds of tasks we're trying to accomplish. So some will have different opinions, and often those differences of opinion center on interpretation. I think many folks trained in statistics are concerned about the pivot toward machine learning because it may seem the machine learning methods lack the interpretability that we've come to expect from classical statistical estimators. So I want to say a bit about interpretation because I believe that actually many of the ways we interpret classical statistical estimators have nice analogs in the machine learning space so that you can get something that's pretty interpretable and perhaps interpretable in the same ways that you've long interpreted your classical statistical approaches. Okay, so the question here is like, is machine learning a black box or can we make something better out of it? And the answer is up here at the top, that you should really report the target estimate, not a model parameter. So when you pivot from something like ordinary least squares to a machine learning estimate, like a generalized additive model or a random forest, the model becomes much more complicated. There are suddenly lots of parameters being estimated, and it's hard to interpret all of them. But often you can convert those parameters into an interpretable estimate of the thing you conducted the analysis to estimate all along. So one example might be an average partial effect. Here on the left, I'm showing an average partial effect for a best fit line, a very simple classical statistics estimator. And on the right, the average partial effect from a generalized additive model. So let's start on the left. At every point here, we can imagine moving across by delta along the x-axis. And if we did that, we could see how far we would have to move up along the y-axis until we hit our best fit line again. We could then say that the difference in that y-axis dimension is f hat, that's our estimated prediction function, of x plus delta, that's this x value here, minus f hat of the first x value. Then the slope, we could say, would be this change in y divided by the change in x. Then as a final step, we could imagine taking the limit as that delta goes to 0. So this is like a pivot from an average slope toward a derivative. But you could just think of this as the average slope in this tiny little window right here, close to the place where we actually saw the data point. And so in the limit as delta goes to 0, we could do that for every one of these data points here. And because this estimator has assumed a line, the answer is actually quite simple. So it ends up being that the change in y per change in x is always beta hat at any point along the line. And thus the average is also beta hat. So now let's go from the statistics estimator at the left toward the machine learning estimator at the right. So now we no longer have a line. We have a smooth curve. It's no longer the case that the average partial effect will be the same at every value of x. You're going to have a steeper slope down here in the bottom left and a much flatter slope up here in the top right. And so you might say, ooh, that's a lot of parameters. It's hard to summarize that. But you could actually do something very similar to what we just did on the left. So you could take each place where you saw data, each value of x, and you could estimate that partial effect at the particular x value. So we get one estimate up here at the right, another estimate here, another here, and on down. And then you could report the average of all those partial effect estimates. And in this case, on the left, you get a number, 1.061, and on the right, you also get a number, 1.513. And I actually think we might prefer the 1.513 because the machine learning estimate has discovered that there's a really steep slope here down at the bottom left, and that's also where a lot of the data exist. Meanwhile, the classical statistical estimator has a best fit line that's heavily influenced by these couple of high leverage points at the top right, and so it has a flatter average slope, even though most of the data is down here at the bottom left, where a steeper average slope might be a better fit. So if we can report the target estimate, we can often come back to an interpretable quantity, even if the prediction function we fit is more complicated than the ones we might have fit with classical statistical methods. I want to close by returning to task clarity. At the beginning, I said that we always have to think carefully about what we're trying to accomplish with our statistical or machine learning analysis, and that what we're trying to accomplish should drive all our choices on beyond that point. So we talked about how you might think about estimating the mean outcome of students in specific classrooms. And then that goal might shape how you think about making a training and test set that includes students from each of those classrooms in both sets. And you might then think about the task as what kind of estimator could predict best for the test set cases, because that estimator would also do well at estimating the average outcome in each class. So that's a nice example because it's very simple and it's something we can all follow and connect to classical ideas in stats and in machine learning. But in practice, if you conduct social science research or you do policy, I think the task is often much more complicated than these simple settings. And it's important to keep in mind how our task that we ultimately aim to accomplish may be different from the thing that our estimator most directly accomplishes for us. So I want to give a couple examples, one about prediction in a new population and one involving causal inference. Okay, so I'm going to first talk about a story at the left, which involves the simplest case, kind of similar to where we started out this talk, then the task at the right, which becomes more complicated. So on the left, we're going to think about prediction in the same population from which the sample was chosen. So suppose we have a sample of students entering some high school. We're going to call it Statsville West High School in 2017. For each student, we observe if they drop out of high school or if they finish and get their diploma. Then we learn a prediction function to see how the characteristics of those students as they entered high school predict whether or not they would drop out before finishing their degree. Then we did this for only a sampled set of students who entered Statsville West in 2017. So we could use our algorithm and predict for new cases who also started in Statsville West in 2017. And you see how what we did here is we learned in a set of cases who were chosen at random from the very same population where we were trying to make predictions. Now let's turn to the right. So suppose you're the principal of Statsville West, and these machine learning researchers come to you and say, oh, we have a good algorithm to predict the likelihood that students will drop out. We trained it on students who entered Statsville West in 2017. And of course, we're now coming to you in 2021 because we had to wait 4 years to see if those students would drop out or if they'd keep going and get their degree. And so you come to the principal and say, like, well, you could use our algorithm and you could predict now for all the students entering Statsville West in 2022, because that's the kids you have now. And maybe our prediction function will help you do something different to help those students to graduate. And if you're the principal of Statsville West, you should have some concerns, because here the target population is not the same as the learning population. In particular, the students who entered Statsville West in 2017 were used to learn the model. But we don't necessarily know that the same patterns will hold for students who enter Statsville West in 2022. For example, you could think about how the coronavirus pandemic affected the outcomes of the students entering Statsville West in 2017 toward the end of their high school experience far differently from how it will affect the students at Statsville West who enter in 2022. So generally, we are always doing this thing where we learn a sample that we have. And then if we're going to use that to make predictions in the future, we are always generalizing to this new target population who happen later than the people we trained the sample on. And this is a reason for caution. When we use machine learning estimators, we have to think a bit about how the social world might have changed between the sample we used for training and the sample we're using for our predictions. A second example where task clarity is really important is when we want to make predictions for a counterfactual population. So in this case, we might say we have a set of units who received a treatment. So maybe they received some extra tutoring at Statsville West. We sample some of them at random, and then in that sample, we learn how their background characteristics predict their outcomes in a world where they received that treatment. But then we want to know, well, there's a bunch of other kids, they didn't get the tutoring. And we'd like to know, like, well, would they also have had better outcomes if they had received tutoring? And we might want to predict the outcomes of those units who did not receive the treatment. And if the treatment was given to people randomly in the population, then this would all be pretty well off because we would have a sample of people from the population at random who received that tutoring, and we predict for other people from the very same population. But suppose that people selected themselves into the tutoring, like students who were really ambitious took the tutoring, or students whose parents knew how to work the system got them into the tutoring. Then the population of units who received the tutoring is going to be very different, possibly, from the set of units who did not receive the tutoring. And it's not at all clear that we can use our prediction function learned among the tutoring people to predict what would have happened to the non-tutoring cases if they had received tutoring. Methods in causal inference make it clear how we can make assumptions and then accomplish these kinds of prediction tasks that work across counterfactual conditions. So to provide a really quick high-level overview, and then I'll open it up for questions in like 2 minutes here. We might think that each case actually has two potential outcomes. So we have, where did my mouse go? Well, I don't have my mouse, but on the left here, we might think that person one has one outcome, like would they graduate from high school in a world where they did not receive tutoring? That's y1 parentheses 0. Then would they graduate from high school in a world where they received tutoring? That's y1 parentheses 1. And it would be really nice if we started by first taking a random sample of cases. This is like randomly choose some kids entering Statsville West in 2017. Then among those cases, it would be nice if we randomly assigned the treatments. So randomly assign them to either receive tutoring or not. So in this case, we have student 1 did not receive tutoring, student 5 did, and student 8 did not. Then you could learn a prediction function to predict the whole table of potential outcomes in the target population, because our cases are a random sample from that learning population, and then the observed outcomes are a random sample of the potential outcomes for all those units. So this works in cases where we have random assignment and random sampling. And it also works in observational settings if we're willing to assume that we can measure some pre-treatment characteristics of people, such that we can find people who look similar along those pre-treatment characteristics, such that we can think of the sampling from the population and the treatment assignments as good as if they had been randomly conducted. And so I think actually this is a great space for the combination of machine learning and social science, because we have tons of questions that really involve shifts to new target populations and also shifts in treatment assignments. And we really need social science expertise to think carefully about those kinds of tasks so that we can realize what sort of assumptions are reasonable. And then given those assumptions, we can use machine learning methods to make predictions and answer the questions about the tasks that we really want to accomplish. So I think I'll stop there and I'll take questions.